Okay, I'm getting started again. Welcome to the afternoon. And I did a very rough overview in the morning, and now I'm going to do again an overview, but a little bit more detailed. In my subject, again, perfect is the clouds and precipitation. And here I'm going to tell you about three different of these very specific packages, like we were talking on lunchtime. We should have a general, future one fits everything, but we don't have that yet. So I'm going to talk about moisture physics. So one parameterization, which is the convection parameterization. And there will be one parameterization that is the microphysics. You would think, well, that's the same thing. And the convection, it must be microphysics, but it's a separate package. And then we have another package to make it even more fun. It's called cloud cover parameterization. And all of these three parameterizations deal with clouds and are entirely separated. So that is how the real model looks like. So let's start with an introduction. We already talked about resolution, resolved, unresolved. So you have resolved clouds. So let's say you have a 10-kilometer resolution model. So on your 10-kilometer grid, you have resolved clouds. And the way our model is set up is that the microphysics deals directly with these clouds that are resolved. Now, the unresolved clouds, they are then treated with the cloud cover parameterization to look into the details that are smaller than your grid scale. And talking about resolution and resolved, unresolved, but there's also two kinds of distinctions one could do between cloud types. So you could talk about convective clouds and more pure turbulent clouds. Clouds often have to do with vertical motion because during vertical motion you have a cooling and then you have some cloud generation that can happen. And you could say, okay, well, if you have a larger scale updrafts, then you call that convection. And if you have a smaller turbulence, then you call them turbulent or smaller scale clouds. But these are then often stratostacks that are horizontally wide, that are internally generated from turbulence. So two different types of clouds and two different kinds of parameterizations. What do you expect? Now, the effects of clouds, precipitation, I mean, they're all pretty obvious. Transport of heat and moisture upwards. You have the impacts of radiation. Low clouds cool the Earth. So maybe we would like to have more low clouds. High clouds warm the atmosphere a little bit because they also reflect solar radiation, but they keep more of the long wave radiation in. And there's a very complicated balance. You can talk to me about that in a coffee break. And latent heat release in the clouds, yeah, that's also important. Now, our cloud parameterization gets informed, you can see it on the right-hand side, gets informed from the convective parameterization and from the turbulence parameterization. So that's a little bit like these two types of clouds having the convective parameterization and the turbulence parameterization, which you heard before lunch. But if you want to have a somehow a little bit unified cloud description, you need to have the inputs from the convection scheme and the turbulence scheme. And that's exactly what we are doing to get our cloud cover. We'll get to that. You've seen this one already, but you just see here again that clouds are very important. Precipitation, radiation, and so on. So we'll start with the first of these three parameterizations, the convection parameterization. And we're using the Titke-Bechtold parameterization from ESMWF. So why do we need a convection scheme? Convection is very good in taking out instability. Now the atmosphere and the model doesn't like vertical instability. So we basically almost never have an unstable atmosphere. And to make sure that happens, convection is the best way to do that in smaller and larger scales. Convection is has continuous scale. There's basically no scale break from very small scales to very large scales in both time and in size. So that makes it very difficult, and we have to make some kind of cut to start the parameterization, the work of the parameterization. Okay. Now let's look at how this convective parameterization works. We do have this one limitation. We have only a single updraft. That's maybe not completely true because we have a deep convective updraft and you have a shallow convective updraft. But at the one single time step, only one of them can work. So that's pretty crazy if you look at the left side picture. If you have grid box with so many little updrafts. So what we consider then is a bulk. We consider this ensemble of updrafts as a bulk updraft. So kind of the mean of all those updrafts, which makes it massively difficult if you have all kinds of different convective events in there. Some events, they only go a kilometer up, like on this picture. Some go very high. Some have unboth structures there. And that's a massive limitation. But there's one or two parameterizations like this Arakawa Schubert paper from 1974. They had already n updrafts in one model step, but that hasn't been taken up. So we have only one updraft. Now let's take a test parcel first. So we run a test parcel from the ground up, and this is being used to check how high the convection can go. Maybe in the picture earlier, you want to know how the highest of the updrafts will go. In some situations, they will stop at mid-levels or even at shallow convection. And sometimes they go all the way to the top of pulse. So that's your test parcel. You started with a little perturbation at the beginning so that it keeps going. And then once you get the information back, how high did it go, then you call this convection either shallow convection, mid-level convection, and or deep convection. So that's the first thing. The second thing is we need to know how massive your convection event is. So that's called the mass flux closure. Very important because that turns it up and down, the convection scheme. And basically, very often a cape closure is. So the larger the tendency of cape creation, the larger the mass flux to reduce the cape creation. That's one typical closure. There's another closure called moisture convergence closure, which measures how much moisture comes in from the side, and we need to do something with it. So bring it up into the mass flux. Also very popular. And there's some other closures. Once you have a closure and mass flux, you know how much goes up. Then you need to know what's going to happen when we move up. And we call that the cloud model or plume model. The entrain and plume model. So the entraining plume model is a little bit like the fruit fly of convection. It's something super simple. Does it work?
I'm just pointing the camera to you.
Okay. So you have this entrain and plume model, which is super simple, and basically you move up with kind of those equations here where you have just the entrainment and the detrainment, and again we have just one updraft, and we want to represent the whole grid box. So once you have that, then you still have to do a little bit more details, put in more details which are on this graph. I've talked a little bit about it in the morning. So for example, the microphysics is going to be very important when basically you want to make precipitation. And how fast does the precipitation gets generated? Is it going to be snow? Is it going to be graupel? So that determines how fast it will hit the ground. And another one is this entrainment and detrainment. So you have a border of this updraft, and inside this updraft you have cloud, yes, but you also have turbulent motion. And entrainment basically means that air comes in from the outside, but basically you turn in laminar air, which is outside, into turbulent air in the cloud. If you look at clouds, you know immediately they're turbulent. So that's another detail that's very important. Convection works in the slow physics package. We've seen the slow physics and the fast physics. So it's applied after n time steps, and then dependency is being applied. What I'm saying here is intermittent behavior. So that's something to keep in mind. You might have chosen your test parcel and your mass flux maybe a little bit too aggressive, so your mass flux is a little bit too large. So what will happen? At the next time step, your cape is gone. It's like, okay, you killed everything. Then the convection is off for one time step, and then it builds up again, cape builds up, and then next time it's on again. So if you're too aggressive, if your mass flux is too large, then you can have this on-off situation, which is numerical not very good. So all kinds of tricks to it. And we want to enter with a few nameless parameters. The entrainment parameter, as you can imagine, is very important. Conversion to water, microphysics, and the access of the parcel on the bottom. The dyno cycle has some description, because over land the dyno cycle is very tricky. The convection wants to start immediately when there is cape, but nature waits for another 2 hours. So a convection scheme often over land summertime, they go off at 10 o'clock in the morning when the sun gives a little bit of heat to the surface. But nature only gives the big rain in the afternoon, which is true over many regions of the Earth. And there have been some improvements by Peter Wächter on that. Convection on-off, you can turn on or off shallow convection. You can tune the height where you make the switch between shallow convection and deep convection, and so on. So we have one package done, and the next thing is I'm going to talk about cloud microphysics. So remember, the convection worked kind of on the subgrid scale, small updrafts of maybe a size of a kilometer in a big grid box, and then these cumulus-induced subsidence. Now, microphysics in the ICANN model is set up such that it only knows the grid mean information. So if there's some small little mini clouds, it won't see it. So that's how we set it up. because I understand that the icon model has its heritage from high-resolution modeling. The role of cloud microphysics, you describe the formation, growth, and sedimentation of water particles. You supply the latent heating back to dynamics, quantitative precipitation forecasting, and then, of course, the radiative intake, aerosol cloud radiation impact effects. Now, one most simple part of the microphysics is the saturation adjustment, which you want to do all the time. So the saturation adjustments does the most simple part. It switches between liquid cloud droplets and water vapor. So as soon as the relative humidity becomes exactly 100%, then you have cloud droplets being created. And then you warm up a little bit your temperature, which means that your cloud drops become a little bit less because it's warmer temperature. So you have to iterate. You have to do a Newton iteration. And this is basically the equation you use for this iteration. So that's energy conservation. So you have latent heating on the second term. And then you have the warming of the environment. So you change saturation, and then you change the temperature, and so on. So this is done twice. I think I said it in the morning. We do saturation adjustment kind of at the beginning of all the physics and at the end of all the physics. So at the beginning, we kind of clean up what happens from dynamics. Maybe there's some supersaturation being created by some motion. And then after all the physics, all kinds of orographic gravity wave drag, or you name it, there could be, again, stuff left over. So you clean up that one more time. Now, there's two different approaches to run the microphysics. And I kind of alluded to that we choose the second one. But the first one, which is, for example, used at ESM-WWF, it runs the numerics first, then the cloud scheme, then microphysics and radiation. So the cloud fraction scheme. So the cloud fraction scheme is the one that knows about the subgrid scale. And so what they do at ESM-WWF, they first define how large is the cloud horizontally. And then you do the microphysics only over that region of your box. While in the icon model, you run the dynamics, then you immediately run the microphysics on the dynamical information horizontal mean over the whole grid box. And then as an add-on, you do the cloud scheme and pass that to radiation. We do use information from boundary layer and convection for that. So I'm going to give you a little bit of an intro to the pieces that play in the microphysics. And we start with the liquid phase. So we have evaporation and condensation of cloud droplets at the saturation adjustment. We have then order conversion and accretion that brings down water and converts them to rain droplets. Now, if you add ice to it, it becomes quite a bit more complicated. But that's how life is. So you might divide cloud ice with snow, even though the threshold is kind of continuous. But you might also want to add graupel or hail. And then you have some conversion processes. All of them are important, and many of them are very complicated. Especially for snow and graupel, the particle properties like particle density and fall speeds are important parameters. Also, the cloud ice fall speed is an important tuning parameter, for example. You have then aggregation processes, so where possibly different particles collide, and you can, of course, maybe most scarily get hail when you have massive updrafts in the convection, and you get long recycling of these growing particles until they become too heavy to sustain. Secondary ice production is something interesting, where you have ice and then it might split into two pieces, and you get more and more and more. And what we have in the model is not one microphysics scheme, but we have 5. Now you have to count through if it was 5 or 6. Now, the first one is the simplest one, which I'm showing here on the right, on the left in the picture. You don't see hail and graupel, so it just has cloud ice and snow as the ice properties. And it was developed for the more larger scale models, like, for example, our global NWP runs with that at 13 kilometer resolution and ensemble at 26 kilometer. The second one is a little bit of a newer development, a further development of that same scheme. And it has the number 3. And it adds 2 moment only to the ice, because Axel feels like for the ice supersaturation, you really need the 2 moments where you not only have a prognostic equation for ice, but also for the number density. So you want to know, once you know the number density, then you also know the size of the ice particles by conclusion. And then you can better describe the supersaturation, which is important for many aspects. But for example, for aircraft flying through areas producing contrails, and we now have a project with Lufthansa where we tell them where not to fly, because we believe that contrails warm the climate, and they are actually flying around them, around these areas. So that's the second scheme. And the third scheme is the graupel scheme. The graupel scheme is adding graupel. And it is used in our high resolution modeling. So for example, the 2 kilometer NWP over Germany, and it's recommended for that. It's still reasonably efficient. And then there are 2 more complicated versions. One of them is the 2 moment, the full 2 moment microphysics scheme. So now we don't do the 2 moment scheme only for ice clouds, but for all the quantities. You can see on the left hand side, it always has an N, NC, NI, NR, and so on. So now you have 12 prognostic variables, and it is quite expensive. But if you really want to have a good description, maybe you're running a research setup for a certain region, and you want to look in all the details on the microphysics, then this scheme is probably where you should go to. And we're also starting to use that one in our rapid update cycle. So that's like the highest, best model at high resolution we have.
So here you say you have 2 prognostic variables. You're not counting in those 12 the regular water vapor, because you always have that in the model.
Yeah, on top of that, yeah. Yes.
What about electrical processes, like the growth of droplets by ion and charge attachment? Electrical processes, charge separation.
We do, of course, need lightning description in our model. I think that's also used for that can be used for data simulation because you have more possibly a lightning data set observations, and then if you have that. But that's an add-on, and it's done afterwards. And I wouldn't know if we change the microphysics. Would you know that? Or would somebody else know it? No. Okay, but
Something for the future.
something to consider. Yeah. And then there's another development from the Israeli Metra service, and they, Pavel Kain, he has implemented a spectral bin microphysics. So spectral means that you divide the spectrum of size, the size distribution in multiple bins, and you can then very detailed describe every single size separately. So you can imagine that will become, if I said the last one was expensive, this one is very expensive. We decided to point that out in red because we're talking about 50 times far slower or something like that, really. But it certainly has some research uses too. So it's in the icon model. Very nice.
The most complicated scheme, does that build on the previous one, or is that an independent development?
That's an independent development, yeah. Which is also nice to have as a comparison, to have a different microphysics. It has not the same heritage at all. Again, the nameless parameters. One very important one is the fall speed of ice particles. So if you let the ice particles settle down a little bit further, then you have a massive impact on the long wave radiation that exits from the top because the temperature changes. You have a fall speed for snow, and you have some scaling factor for intercept, for raindrops. Okay, so we have multiple choices, and you can always ask, which one is suitable for your option, but the most simple one for global is the number 1, and for local areas, I use the number 3, which is called the global scheme. So then clouds. The cloud cover, so that's the third package, the last one of the 3 I'm going to cover. Why do we need a cloud scheme? Well, I mean, I think the question is ridiculous because we obviously need these very small scales. We've looked at the picture. We cannot resolve all of that, certainly with a 13-kilometer global model. And even if you go to a higher resolution, you need some description of the smaller scales. And already in the picture, you can see with the eye that solar radiation seems to be a big issue because our eye can see all these differences. And the mean will not give you the same radiation. It's nonlinear, massively nonlinear. So some notation, the prognostic variables, they are the ones that the microphysics sees. So you have prognostic cloud, water, ice, and the other quantities if you have them, rain, snow. And then you have, you could imagine a total water. For liquid, that would be water vapor plus cloud liquid water. So if we add that together, saturation adjustment works only with these 2, and it will keep QT, this total water, as a constant. Even if you change between vapor and cloud, you need to conserve QT in this case. And then you can do stuff with that. And then, on the other hand, there is the diagnostic quantities. The diagnostic quantities, we call them because the cloud scheme is a diagnostic cloud scheme. So we have the variables coming out of the cloud scheme that gives you subgrid clouds, and they are not the same, obviously, as the grid scale clouds. So that's an important thing to remember. Okay, we realize that we have convective and turbulent source terms. The cloud scheme divides up in the convective and turbulent. So here is the description of the turbulent contribution to the cloud. And that's basically anvils. That's basically things coming out of the convection. So you have the updraft, and then you hit some kind of stable situation, and it moves out. And this equation basically is a volume conservation. So you have a volume of air coming out, and you have a volume of your grid box. You know, how many 100 meters high and 13 kilometers square. So you have a volume, and that you know exactly how much volume you pump out of your convection and how long will it take to fill it up. So that's basically the entrainment term here. You can see the D term here. And you have to have some constants, and you only do that over the cloud-free area that you add some cloud. And then what you have is you have a decay term. So you have some kind of turbulent or other effects that will decay the cloud. And we describe that massively simple by just putting a decay timescale on it, 1,500 seconds. You can change that. So that's what I called also hand waving beforehand in the morning. But it's a simple setup. And in this equation, we even throw out the prognostic term, the prognostic term on the left-hand side. So we say this whole thing is in equilibrium. We constantly blow in air from the anvil, from the convection, and we constantly slowly decay. And then we can write down an instant diagnostic balance of cloud cover. And the second component of this description is the turbulence. So you have some turbulent motion and turbulent information about the variance of total water, so the amount of water that exists in the liquid phase. And if you then put your saturation mixing ratio, QS here, and you have total water marked in the vertical on the left side picture, then you can just see if there's some variability. You will have some smaller clouds which are in this shaded area here, yeah? So that will be one grid box, and you have some little clouds there. You can also describe that on a PDF of total water. So I have drawn down some kind of semi-Gaussian PDF, which is maybe similar to what we're using. And again, if you put your saturation mixing ratio here, now it's on the bottom scale, QS, then you can read off on the right-hand side the shaded area. That's all cloud term. So if you have knowledge of your variance and your PDF, how the PDF looks like, it could look completely different, then you're in business. And that PDF, truly, there's different papers that have some assumptions of PDFs that can be as different as a triangle, like a scheme in the Met Office from Smith, or a box top hat function, or Gaussian, double Gaussian, you name it. So the possibilities are plentiful. And what we have is these kind of two parameters. One is the variance here, and one is the asymmetry factor. So that kind of tells you how skewed this, how big the tail is on the right-hand side of these PDFs. And obviously, the variance tells you how wide the distribution is. That's the key thing you need to know. So basically, with that, we have a convective cloud, we have a turbulent cloud, and the cloud scheme is finished. We have a little add-on, tiny add-on, which is condensation. So now these are small little clouds that happen in the subgrid scale. And one idea by Günther Zwingler was, physically, they should also contribute a little bit latent heating to the model. And we've introduced an option. You can turn it on if you want. It has a little bit of an impact. Yeah, with that, I'll come to the nameless. First, on-off. So you can turn the cloud scheme off. So basically, there's no clouds going to radiation. You can turn it on with 1, or there's another good option, 5. When you do run at high resolution, like an LES, then maybe it's a good thing to really have a 1-0 cloud cover scheme, like we also use for the microphysics. So then you're consistent with the microphysics again. And there's a few other parameters which you can look through. One gives you the asymmetry. One tells you something about the variance and how that's determined. And if you want to turn on this condensation or not. Yeah, so with that, I'll finish up. Thank you so much.